Okay, Assalamu alaikum. So today, basically, we will continue with the talking about the differential amplifiers, the CMOS one. So if you remember this amplifier, yes, and this is the VN1, VN2, and we're taking the output as the difference between those 2 points. This is RD, and this is, so this was the basic differential amplifier that we have. We can also create a differential amplifier through the use of a PMOS device. So we have a current source here on top. And then we have the PMOS, the BN1 here. Let me draw it differently. BN1, and then BN2, and another PMOS. And we can have here either a resistor or a current source. VB and the same VB here. Okay, and this is ISS. So we can create a differential amplifier with the input coming on the NMOS devices, or they can be coming on the PMOS device. Many times you will find that they use the PMOS input devices because they have better noise performance compared to the NMOS, but this is out on this before we proceed further. Okay, so today basically will differential amplifier we have discussed earlier, so we will not cover any new topic. Start with example number 1. So we want to find the gain. Assume lambda equals to 0. Find the gain for this circuit. Let me just draw it. We have another current source down here, another current source here. This is called RD. This is called RSS. And we're taking V out from here. It's VN1 and this is VN2. Okay, so we want to find the differential gain of this circuit. So if you remember, when we want to find this gain, what do? We basically draw a symmetry line. No. We draw, that is basically across the circuit, and the circuit is symmetric across this line. So, and every point on the circuit, we mentioned earlier that it acts as a virtual ground. So it's not a real ground, but it's connected. So in the middle here of this resistor, there is a ground. In the middle of this resistor, there is a ground. What does this mean? What does this mean is that now we can draw half a circuit. So we can have half circuit. What do I replace this RD? We replace it with a resistor that's RDD over 2 and a ground here. I'll go again through this. And then we have VN here and another half circuit RSS over 2 and the current source here, which is the original that was here. So now, since the line of symmetry is cutting the resistor in the middle, you can replace of its value. Means, isn't it the same if I draw a circuit of RDD over 2 and RDD over 2? Isn't it equivalent to RDD? I mean, there are two resistors in series. Each one of them is half of RDD. And if I make it either this one, number 1, or number 2, they are both equal to each other. So once when the line of symmetry, a ground here in the middle, and then we can replace it with a half circuit equivalent model. Any question on this? Okay, so when you have a half circuit model, basically then you take half of the resistor. When the line of symmetry crosses a resistor, you can just replace it with a resistor over 2. Okay, now we can find the gain for this half circuit. So if we look at it, it's basically looks like a common source with degeneration, and that the standard gain of a common source with degeneration is basically minus RD over 1 over GM plus RS. So what is my RD here? It is minus it is RDD over 2 divided by 1 over GM. My RS here is RSS over 2. And this is the gain for this circuit of the entire differential amplifier. Any question on this? Okay, we can move further. And now let's take a few more examples. Now we will basically see that we can also have a cascades in our differential amplifier in order to get higher gains and output impedance. So let's see this. So that's also the same. Just a note, when you want to draw the line of symmetry, this one be exactly identical to each other. We cannot make a line of symmetry if they are, and assume a virtually grounds if they are not symmetric across this line. Only this assumption is valid if the circuit is basically exact replica of each other. And we can take the B output from here. Okay, so let me just give the names of the transistor M1, M2, M3, and M4. And this is ISS, and this is VDG. Okay, so now we want to find the gain of this this differential amplifier. So since both sides of it are symmetric, we can draw the symmetry line. And we said any point lies on this symmetry lines will be turned to a virtual ground, and then we can draw half of the circuit. So we will just have this. M3, this, you can take either halves and find just the gain for that half because both are symmetric. So now what is the gain? The gain, it looks like a cascade amplifier. So the gain is just minus GM1 times what? Times the output impedance that we see. So what do we see here? If we look up, we see an infinite impedance because it looks like an ideal current source. And if we look down, we see a cascode having an impedance of GM3, R out 3 almost, R out right. So now the gain will be minus GM1 times the output impedance, which is just going to be GM3, R out 3. This is GM3. Okay, so this is the gain of the amplifier that we are having here. Any question on it? Okay. Now, this is so small. Let's move further. It will take just some time to draw it. Here means that when I draw this line, that they share the same biasing voltage. Oh, sorry, mistake here. No, not mistake, it's fine. Just put it with the other direction. It's M2, M1, VN1, VN2, and this is VB1, VB2, VB3, and this is M3, M4, M5, M6, M7, and M8. This amplifier, we usually call it telescopic cascode. You know, it looks like like a telescope. That's why it has the name of telescopic amplifier. So usually it's good for high gain, but it does not give us very large swing on the output. The output is taken from here. Because, I mean, you have this cascode, they consume a lot of, they consume voltage drop. So our signal cannot reach to the maximum of supply after. Okay, so now we want to find the gain of this telescopic cascode. So what do? Since it's identical on both sides, we can draw a line of symmetry. And any point on this line of symmetry crossing is going to be a virtual ground. Now, if somebody is asked, might think, what about those lines which I draw here? In any case, those are a biasing points by a DC point that will turn out to AC ground in the small signal. So again, we can just draw a model. This is VN, VB1, VB2, and VB3, M7, M5, M3, and M1, and the V out is here. So in order to find the gain, we just look at this half of the circuit, and it's a cascode amplifier where the gain is going to be minus, why it's not, minus GM1 multiplied with the output impedance. So what do we see? An R on ROP up and RON down, that they are in parallel with each other. So it will be RON in parallel with the ROP. Now let's find RON and ROP. So RON, it's a cascode of an NMOS. That will be GM3, R out almost, Why it's not typing quickly? R out 3, R out 1, and ROP, it will be GM5, RO5, RO7. Okay. Any question on this? Okay, no question. Can move forward. And where is my charger? Okay, just give me one. Okay. Any question on this? Okay, let's take further example. So this similar to the exam resistor R1 that is coming in parallel of the transistors M5 and M6. So now we want to find the output is taken from here. We want to find the gain of this telescopic cascade. So since it's symmetric on both sides, we can draw a line of symmetry. And any point that cross it will be connected to a virtual ground. So now the gain can be just by looking at half of the circuit. I don't have to draw it again because it's too big. So the gain will be minus GM1. Yeah, if you want to think yourself about the gain, so what do you expect that change will happen here? So again, we will have RON in parallel with ROP. Who's going to, none of them will change, do you expect? Or no expectation? So what is going to change is that since the addition of R1, yes, ROP will change. And that's excellent. Why? Do you know what change is happening now? R1 is, what is doing? Basically, R1 appearing in parallel of whom? In parallel with M5. And M5, we see from it, R out 5. Yes, excellent. Yes, thank you. So that is what's going to happen. So it will be minus GM1 times RON is the same as GM3, R out 3, R out 1. And all of this in parallel with R out B, which is GM5. R out 5 now will become in parallel with the R1 multiplied with the R out 7. Okay, now this is the simplified version. I mean, you can also write here that this is plus RO5 and par with RO1 plus RO7. But if you don't include even this part, it's still fine. Thank you. Any question on this? So the only change is that R1 is appearing now in parallel with the R out 5. So this is what we are going to change from the previous question. Let's see more examples. If you have any question, I can pause and take the question. Okay, let's see this one. This is also, we have here another transistor. Another transistor here. M6 VB, and this is M4. This is connected. This is M3, and this is another. And the B output is taken from here. Okay, so now we want to find the gain for the circuit. Lambda is greater than 0, means we need to consider the R outs. Okay, any idea? I mean, it's exact replica across a line of symmetry that we can draw here. We can have this as a virtually ground, and we can find the gain for half of the circuit. So M5 and M is your name. I only see your ID number. Obed, yes. Yeah, it's good to write your number so I can call you by the name. Yeah, Obed is excellent. M3 and M5, they are in parallel, and M3 is a diode connected, 100% correct. So our gain is going to be minus GM. This is M1 times the R out. The R out, we see down, R out parallel with those transistors that they are both up, which is I'm in parallel with the R out 3. And M5, we are looking from its drain side. Therefore, we will just see R out 5. Is that clear to everybody? This we should be now, ideally speaking, experienced about these ones. So this is going to be in parallel with the R out 5, in parallel with the 1 over GM3, in parallel with the R out 3. Okay, let's move on and take further example. Okay, now I want everyone to try to do this and then share the answer with me. This is R1 and this is R1. And this line is basically connected here and here. This is PN1 and yes, we called it M1. This is M3 and this is M4. Okay, I'm pausing here for a minute. Okay, so now we can have our, oh no, can have our line of symmetry. So we have this point crossing the line of symmetry, and we have this is crossing line of symmetry, and this one is also, it's the same point ideally. It's also crossing the line of symmetry, so we can just replace it with the half circuit that will look something like this. And we have R1 here to ground. This is grounded. And then we have here the M1 with the V, and V out is taken from here. Okay, so the gain will be minus GM1 times the output impedance that we see here. So here we are seeing R out 3. From this one, we are seeing R1. And down here, we are saying R out. So R out 1 in parallel with R1 in parallel with the R out 3. Any question? Yeah, let's move further. Let's see, one more example. Okay, let's see here. Let's fix my drawing. RSS. And we have here current source and another ideal current source, 2 and 1. One B out and 4 and 3, and this is VB. Okay, so let's think for a second about this one too. So let's do it. We will draw the line of symmetry, and this point in the middle will have a virtual ground. So okay, so now this looks like a common source with degeneration that has again standard gain relation, common source with degeneration. If you remember, it has the gain minus RD over 1 plus GM plus RS. Now you may also open the like Obed did get read from the GM down, so it will go up, and the expression will change, but it's still correct. Whichever one you want to use, both of them are fine. So we will have our RD here, this transistor M3. We have here R out 1 to make sure that it's going to be a cascade. So different thing. Is R out. I want to write in the red. Minus R out 3 over 1 S over 2. Okay, which is also equivalent to minus GM 1 R out 3 divided by 1 over 2. Both of them are equivalent expression. Any question? Okay, let's do further. Example. For revising the previous topologies again. So this is VB M3. So this is M2, this is M1. Yes, there is RS here and there is an RS here. First time you see this RS comes up here. Okay, I am again giving you a minute to try to solve this. Okay, so we will draw our circuit line, and the point here in the middle of RSS is going to be grounded. So our circuit will look something like this, the half circuit. It's RSS over 2. This is the VN and the V out, and this is RS. So now to identify what type of circuit it is, again, it's a common source with degeneration. We all agree on that, yes, because our source of this transistor, M1, which is the main in the amplification, is basically not grounded. And so the standard, again, gain, we said it's minus RD over 1 over GM plus RS. Basically, we draw the line of symmetry each other. They are exact replica of each other. And this one, how we find it, RSS over 2, we talked about it in the beginning of the class. So it's like have each one of them is RSS over 2. This is equivalent to have a single resistor for RSS. Means two resistors on series, they are half, they are equivalent to one complete of this resistor RSS. It's half plus half is equal to 1. So if I cut the first line here in the middle and then replace it with the ground, okay, so now I just want to know what is my RD here. My RD is the impedance that I am seeing up. So if we look at it, it again look like a cascade, if you remember. So this impedance up is GM3, almost GM3, R out 3 times RS. To be more exact, it is GM3, R out 3, RS plus RS plus R out 3. Do you see this? This is the trick in the question here. Is this clear? This is the only difference that we have. So this we for. So this is the first time that we have. So the trick is to know that the impedance up here, our RD is like this, and our RS here is just this RS. As this clear to everybody? Any question on this? So the gain will become minus GM3 R out 3 RS plus 1 over GM1 plus RSS over 2 in a simplified way. If you want to be more exact, then add the RS here plus the R out 3. The circuit is exact copy of each other. If it is not exact copy, then life become difficult, and we need another techniques and the good news that I am not going to examine you in that scenario, because that is something extra tiring for you. But at least if it is exact replica, I want you to be able to you cannot just write it as an RD unless you explain to me what is your RD here. That is the general expression. If your transistor, when we, you don't have a mic to understand. No, you cannot write R out 3 plus RS as your RD. Here, basically, it's a cascade topology. You have to be careful. They are not in series of each other. We have discussed earlier that if scenario, looking, this is M1, is going to be the exact expression is GM1 R out 1 RS plus RS plus R out 1. If you do R out equals to R out 1 plus RS as if they were in series, this is wrong. They are not in series. How did we know this, that this is the correct expression? We derived it in an earlier lecture from the small. Okay. I hope that I answered your question. Okay, thank you. if we are providing input at the source and taking output at the drain, what will be our output in this case? Let me go back here. Your question was if, sorry, and there is a source here, whether it is or not, and your input is taken from here, Vn, and the V out is from here, and I need to find R out. Yes, this is the question, Jamshed. Yes, okay. Now you remember this is an RS here. Now, in order to find the output impedance, we did two main things. The first is that we need to short the input and apply a test with the current IT. So you will end up with the same impedance that is here, the cascade relation. Why? Because when we find the output impedance, we must short two steps that we do. We short the input side, we apply a test source from the output direction with VT and have a current IT, and your output impedance is VT divided by IT. Are the same. Clear? Okay, thank you. Now I want to do more a design question with you with the numbers. How much time do we have? Okay, we have still 15 minutes. Let's do design with numbers. Okay, so the question is asking that we should design a differential pair. Right. So it's an other RD, and this is VN1, and this is VN2, and we're taking output from here. Okay. Yes. So this, we need to design this amplifier for overdrive voltage of 100 millivolt. We have a power of 2 milliwatt. We need to select RD to place the transistor at the edge of triode region for an input common mode level of 1 volt. Assume lambda equals 0 and microamp per volt square. We have V threshold equal 0.5 volt of the NMOS, and VDD equal 1 thing. Okay, so these are the things. Yes, the two sides are symmetric. If you make a vertical line in the middle, and they are exact replica of each other across this line, like a mirror here, which is in this case, they are fine. So basically, let's solve this question. Any question on the question before? Okay, let's proceed. Just want to remind you with the equilibrium overdrive voltage relation that it is basically this relation V JS minus V threshold equilibrium equals to square root of ISS over mu1 COX W over L. Okay, so first, like, yes, Tuba, you have a question?
That, I need to place a transistor at the edge of the triode region. Now, what does this mean by the end of triode region?
Means that you are applying a VGS that's equal, like you have this relation. You remember that VDS should be greater than or equal, yes? Let me fix it. Okay. So when we are saying that it's at the edge of the triad region, means that VDS equals to VGS minus V threshold. Not an of triode. Means if little bit it reduce VDS, then we are leaving the saturation region and going into the triode region. Is that clear?
Yes, ma'am. Thank you, ma'am.
Okay, this is for the saturation. So let's keep these things in our mind. Edge of triode means that our VDS is equal to the VGS minus V threshold. Okay, so now what should we do? We need basically to find W over L is not known, RD is not known, ISS is not known. All of these are do is that we have the power consumption is equal to what? Yes, it's VDD times ISS, not a single ID, because I have an ID here and I have an ID here, that they will both meet together and form ISS equals ID plus ID plus 2ID. Because both of those branches, they are drawing current from the supply voltage, but the total current is equal to ISS. Is that clear? Okay. ISS, and we can find ISS equals how much this will become. Is that clear to everybody? Any question on this? So always trick from the power. We have two branches of the current. The total current will be equal to ISS, and therefore we found ISS value. Now you can see that in this relation, we are given the equilibrium voltage, 100 millivolt. We know ISS, we know mu1 COX, we can find W over L ratio. Is that clear? Okay, so now from here, we can find W over L by substituting this one as 100 millivolt and square root of ISS milliamp. Sorry, I am 10 to power minus 6 times W over L. From here, we find W over L to be how much I did the funny number. 1011 and 0.1. This is it does not have a unit because the ratio of dimensions. Okay. Now, so we find W over R, we find ISS, we are left with RD and the gain. Any question?
Ma'am, what is
Yes.
BVG?
What is yeah, that's VGS. Thank you for correcting. I brought it from. Okay, now let's continue. We need to find RD and we need to find the gain. Now this looks like a useful thing here. Now VDS is basically equal, if you remember, RD equal to VGS is equal to the V common mode of the input that is applied here. VCMN minus V threshold. Now I can cancel this VS with the VS. Okay, because in the this large signal analysis, we don't make the virtually ground. That just for finding the gain. So that's over 2. Where I wrote it here. So this is 1 volt minus V threshold. Here, from solving this equation, we find RD to become how much? 2.34 kilo ohm. Again, minus, sorry. The gain D in per RD, no R out. Why? Because lambda is equal to 0. And therefore GM is 2 mu n COX W over L ID times the RD. Now we know the ID, we know W over L, we know mu n COX, we know this is 2. We can find the gain, and we have found from here the RD. So you will substitute all these numbers, and we will get a gain to equal minus 25.74. No unit for the gain. Now let me revise again the steps that I followed. So the question was giving me the equilibrium overdrive voltage. We have wrote the equation for it, VGS minus V threshold equal to the square root of ISS divided by mu n COX W over L. Now, after finding from the power relation, we found the ISS. We substitute to this equilibrium overdrive voltage, and we found W over L. Now, after that, we are moved to find VDD. RD. RD, we find it from the information that was given about the edge of triode region. So our VGS equal to the VGS minus V threshold. VGS is basically given from the common mode input minus the source voltage ID times RD minus the VS. Since both sides have the VS, we are remained with a similar relation. We found RD from here, and then our gain is minus GM RD. We found GM, and we know RD, and we found the gain. This is the story. I know it's boring. This is how it is. Any question on this? Any step is not clear? Okay. There is a question. I'll just tell 1 second, give me. There is a question 90 in the book in page 533. So again, question 533. It's about design of a telescopic amplifier. Please try to do it yourself. It has a lot of calculation steps, but it's nice to try to design a telescopic amplifier, and let me know if you find any issue in solving it. Okay? Yes, your question, I'll answer first. Can you repeat what common mode means? Common mode means it's the average value or the DC value potential signals. So this is VN1 and this is VN2. This they are different, so they have 180-degree phase difference from each other. So this is VN2. So V1 and VN1 and VN2, they are differential signal that they have 180-degree phase shift from each, but they have the same average DC value, which we call it the V common mode. So if we draw this is time and this is voltage. Let's say this is V common mode is 0.9 or 0.8 volt if our supply VDD is 1.8 volt. Okay, and this the amplitude AC amplitude, so they can go, let's say, to the here this point 0.91 and here 0.89. So the maximum the AC signal, the maximum amplitude it can 0.02 millivolt. You can see the peak to peak amplitude of the AC signal, but it has it's not airing at a DC voltage. So it's not around the zero, it's at a certain DC voltage around it. And that DC voltage, we call it the common mode. That is the average of both of those two signals. Is that clear? Okay. Now, a question from Tanzil. In half circuit model, we find gain for half of the circuit, so the total gain will be double or the same, will remain the same? No, not double. It will be the same as the gain of the half of the circuit. It just, how to say, the gain will be the one that we find for half of the circuit, no doubling for it. Because we are working on this differential signal, so that's why we are having the gain is equal to the gain of the half of the circuit and not double of it. Are both, let's say the first half of the circuit will amplify for VN1, the differential signal VN1. The other half will amplify for VN2. You will the gain that is equivalent to the total of the circuit. I'll try to show you with if I can do a simulation and show you this with a simulation next time. I'll show you a demo of it. Okay, but they are, one is amplifying the one input, the other is amplifying the other inputs. Okay, thank you. Any other question? please try just to do that design question, and let me know if you face any difficulty so that we can try to clarify it. Because in the exam, we will have also some questions that they are hand calculations, and some that they will be just by looking, you should be able to figure out the question. Okay, see you. Don't forget tomorrow the session for the tutorial. Otherwise, you can see the recording if you are not available that time. Okay.